Imagine a line, a simple, uninterrupted line that extends to infinity. This line, in its purest form, represents the first dimension, a realm of length without depth, an infinitely long, impossibly thin universe. Now let's expand our perspective and introduce a second line that intersects with the first, and suddenly we find ourselves in the realm of the second dimension, a plane where length and width interact in harmony, but depth remains a variable foreign to them. When going up into the realm of the second dimension, a plane where length and width interact in harmony, depth remains a variable foreign to them. By taking one more step, we find ourselves in the familiar third dimension. This is where depth comes into play, adding volume to our world. Buildings rise, valleys deepen, and the universe acquires shape and texture. But what if we go to another layer? Time is the elusive fourth dimension that permeates our three-dimensional space, invisible but omnipresent, which dictates the rhythm of our lives, a continuous thread that connects each previous moment with the current one and the current one with the next. In this realm, our understanding of reality becomes broader and more complex. Here, the very fabric of the universe reveals its complexity, hinting at dimensions beyond our perception. However, nature hints at even more complex dimensions in physics. The theory suggests the existence of dimensions beyond our perception, necessary for the fundamental forces governing the universe. These higher dimensions, although beyond our perception, are crucial for understanding the structure of the cosmos. Join us today as we try to unravel its mysteries together, dimension by dimension. Music. Music. In a historical context, the concept of measurement permeates all human thought, from the abstract reflections of ancient philosophers to the revolutionary discoveries of physics. The philosophers reflected in their day on existence, laying the foundations for our understanding of space. In their debates, they questioned the very essence of reality, imagining realms beyond the tangible. Unlike their more evolved counterparts, these newly discovered galaxies have distinctive characteristics that set them apart. Meet the visionary Hermann Minkowski, who irrevocably changed our understanding by proposing that time and space are not separate entities, but intertwined dimensions forming the fabric of space-time. Albert Einstein, in turn, building on the foundations established by Minkowski, presented the evolutionary theory of general relativity, restructuring our understanding of gravity, space, and time in a single continuum, forever changing the course of physics. Thus, from the philosophical quest of ancient thinkers to the scientific revolutions caused by Minkowski and Einstein, the journey through spatial thought reveals an incessant quest to understand the true nature of our universe. Thus, over time, we have come to understand that to truly understand the fabric of our reality, we must go beyond the three tangible dimensions and delve into the fourth dimension, time. The concept of time as a dimension is profound and compelling for our existence and for the universe. Unlike the three spatial dimensions, time has a direction. It advances inexorably from the past, through the present, and into the future. This unidirectional flow of time distinguishes it from space and provides the universe with a temporal structure that is fundamental to our understanding of reality. To illustrate the importance of time as a dimension, let's consider a simple, everyday scenario: organizing a meeting. When we suggest to someone that we meet in a certain place, we unconsciously navigate the three basic spatial dimensions to determine where it makes sense to meet. If we were to arrive at different places, the meeting would not occur. However, the dimension without which the meeting would not take place is no less important. If you arrive with your friend at the same place but at different time intervals, you will not be able to see each other. This entanglement of space and time is manifested in the concept of a world line, the path that an object or person travels through space-time, representing its history and future. The idea of world lines provides a vivid illustration of how events are linked in the fabric of space-time. For two people to meet, their world lines must intersect at a precise point in space and time. This intersection is not just a coordinate, but a space-time coordinate, the only point in the vast continuum of the universe where both the where and the when coincide. This principle applies not only to simple encounters, but also to the fundamental functioning of the cosmos. Celestial bodies, from planets to stars, trace their own world lines through space-time, their trajectories determined by the interaction of spatial positions and temporal moments. For example, Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect. Earth's orbit around the Sun is not just a path through space, but a continuous journey through time, with each point in the orbit representing a unique moment. The integration of time as a dimension has a profound effect on our perception of the universe. It forces us to look beyond static images of space toward the dynamic development of events. Time allows us to understand the universe not as a set of individual moments, but as a continuous narrative in which cause and effect unite our reality into a coherent whole. The inclusion of time as a dimension has catalyzed significant advances in physics, particularly through Einstein's theories of relativity, which we have already mentioned. These theories not only deepened our understanding of the cosmos, but also paved the way for new research in cosmology and quantum mechanics. Einstein's revelation that time is relative, that it slows down or contracts depending on the speed of an object, challenges the idea of a universal clock. This concept, rooted in the special theory of relativity, illustrates how the passage of time changes for observers in different frames of reference. This phenomenon is confirmed by experiments, for example, with atomic clocks on airplanes moving at high speeds. In quantum mechanics, time as a dimension underlies the evolution of the state of particles, governed by the Schrödinger equation. This basis is important for understanding phenomena, such as entanglement and superposition, where the temporal dimension provides a probability distribution of outcomes. Going beyond the fourth dimension opens the door to a realm in which our everyday experience and the laws of physics, as we know them, are fundamentally questioned and expanded in the search for a unified theory that harmonizes the principles of quantum mechanics and the general theory of relativity. Physicists have ventured into the theoretical landscape of higher dimensions, where the fabric of the universe becomes more intricate and mysterious. The fifth dimension and beyond are not only speculative constructions, but also important components in the search for a deeper understanding of the universe in theories such as string theory. These higher dimensions offer solutions to the most challenging mysteries in physics, including the unification of fundamental forces and the nature of gravity at quantum scales. The difficulty in visualizing higher dimensions lies in the fact that our perception is inherently three-dimensional, so analogies become an invaluable tool. One of the classic analogies to help understand the concept of higher dimensions is to imagine the perspective of a two-dimensional being, often called planetaro, who lives in a flat, two-dimensional world. This being can move forward and backward, to the left and to the right, but has no concept of moving up and down, since these dimensions do not exist in its two-dimensional experience. Let's imagine a three-dimensional sphere crossing this two-dimensional world. For a planetaro, the sphere would first appear as a point when the sphere barely touches the two-dimensional plane, gradually increasing until it becomes a circle as more of the sphere crosses the plane, and then it would shrink back to a point as the sphere leaves the plane before disappearing completely. A two-dimensional being would perceive this event as a circle that appears out of nowhere, changes size, and then disappears without realizing what three-dimensional object is causing the phenomenon. String theory, the leading candidate for a unified theory, postulates that particles are not the individual points we see, but small vibrating strings whose modes of vibration determine their properties. This theory requires the existence of more than the four known dimensions. In fact, it suggests that there may be up to 10 or 11. These additional dimensions are compacted or convoluted so that they're imperceptible at our scale, like the sphere in the example of flatland. In the fifth dimension, we find a space that contains all possible universes that start from the same initial conditions as our own. Let's imagine a tree in which each branch represents a decision or a different result that leads to a different reality, all of them coming from the same trunk, just as a person at the base of the tree can choose which branch to climb. A being with access to the fifth dimension can explore these alternative realities, each a variation of our own universe, but with slightly different results. The ascent to the sixth dimension opens a plane that contains all possible universes with the same initial conditions as ours, but with any possible set of physical laws. If we think of each universe as a sheet of paper, the sixth dimension would be like a stack of sheets, each representing a different universe. A being capable of traveling through the sixth dimension could jump between these universes, learning the different results and the laws that govern each reality. The seventh dimension expands this concept to include universes that start from different initial conditions. Using an analogy with a library, each book represents a different universe. The seventh dimension encompasses the entire library, offering not only different stories, universes with the same initial conditions as ours, but with different results, but also universes with completely different initial conditions. A seven-dimensional being could move through this library, experiencing an infinite number of universes, each with its own initial conditions and unique physical laws. In the eighth dimension, we find a network of all possible universes, each with its own initial conditions and physical laws, as well as all possible variants of its development over time. Let's imagine a huge network in which each thread represents the timeline of a universe. And physical laws. In the eighth dimension, we find a network of all possible universes, each with its own initial conditions and physical laws, as well as all possible variants of its development over time. Imagine a huge network in which each thread represents the timeline of an independent universe, and each node where the threads cross represents an important event that could lead to the branching of new universes. The eighth dimension encompasses this entire network, allowing one to travel between any node and explore the connections between the different universes and their history. As we approach the ninth dimension, we find all possible physical laws and initial conditions that have ever existed or will ever exist. This dimension can be compared to the art of origami, in which a single sheet of paper can be folded to create numerous shapes. Each fold represents a change in the initial conditions or in the laws of the universe, and the ninth dimension includes all possible combinations of folds, resulting in all conceivable and inconceivable universes. A being that lives in the ninth dimension will not only have absolute freedom to cross the boundaries between all possible realities, but will experience all existence and all its possible variations. The 10th dimension is the pinnacle of the hierarchy of dimensions, where all possible outcomes, realities, and existences converge. It is the space that encompasses all conceivable and inconceivable timelines for every conceivable universe, effectively encompassing all possibilities of existence and non-existence. This concept can be visualized as an infinitely complex branching tree or network, where each branch represents a different outcome or timeline, and all branches ultimately converge at one point, the 10th dimension. Visualizing the 10th dimension is a challenge because of its abstract nature. One approach is to use the analogy of a tree, where each branch represents a different timeline or universe, and each leaf represents a possible outcome within the universe. As we move from the trunk to the leaves, we move from the initial conditions of the universe, the lower dimensions, through the various choices and events, the higher dimensions, that lead to all possible outcomes. The 10th dimension represents the point at which all these possibilities come together, the singularity of infinite potential outcomes. This suggests a cosmos in which all possible outcomes can not only occur, but do occur in some timeline or universe within the 10th dimension. The concept itself invites us to reflect on the immensity of possibilities that lie beyond our observable universe. It raises questions about destiny, choice, and the underlying structure of the cosmos, leading to a broader exploration of the potential realities that may exist beyond our immediate perception. The exploration of higher dimensions beyond our familiar three-dimensional space and four-dimensional time has profound implications for both physics and cosmology. This field of study is not only designed to challenge our fundamental understanding of the universe, but may also hold the key to uniting the disparate forces of nature, potentially resolving some of the, since recognizing the existence of higher dimensions plays a key role in the search for a theory of everything, a single framework that perfectly unifies general relativity and quantum mechanics. Currently, these two pillars of modern physics describe the cosmos on very different scales and in seemingly incompatible terms. General relativity perfectly explains the gravitational interaction of massive celestial bodies, while quantum mechanics reveals the interdimensional world of subatomic particles. Higher dimensions can also offer new insights into cosmological mysteries, such as dark matter, dark energy, and the nature of black holes. For example, some theories suggest that what we perceive as dark matter could be gravitational effects of matter in parallel branches, a concept of M-theory that suggests the existence of multiple membranes or parallel branes as fundamental components of the universe, each of which could contain another universe in higher dimensions. Looking ahead, in the field of energy, mastering the complexities of higher dimensions could pave the way for harnessing forms and mechanisms of energy that we cannot even imagine now, and that could lead to the creation of clean and virtually inexhaustible energy sources. Similarly, the field of space travel could be revolutionized with a better understanding of the structure of space-time, which could ultimately allow the creation of not even imagine, and that could lead to the creation of clean and virtually inexhaustible energy sources. Similarly, the field of space travel could be revolutionized with a better understanding of the structure of space-time, which may ultimately allow warp drives or other forms of faster-than-light travel. These are concepts that currently belong to the realm of science fiction, but that could be theoretically plausible in higher dimensions. The search for higher dimensions is already underway. Researchers are exploring the subatomic world with particle accelerators, such as CERN's Large Hadron Collider, in search of evidence of additional dimensions and the particles that could inhabit them. This experimental work is complemented by theoretical studies that immerse physicists and mathematicians in the abstract realms of high-dimensional space. As we complete our journey through the dimensions, from the simplicity of a line that extends to infinity to the unfathomable complexity of the 10th dimension, we face the challenge of visualizing spaces beyond our three-dimensional experience. Through mathematics, we can describe the properties and relationships within higher dimensions, and physics offers theories such as string theory and M-theory, which point to the existence of these additional dimensions. Animations like Tay-Sachs allow us to conceptualize high-dimensional shapes and their projections or shadows in lower dimensions. Further exploration of higher dimensions promises to revolutionize our understanding of the universe, just as the transition from flat Earth to a spherical one centuries ago broadened humanity's horizons. This expanded perception has the potential to influence not only science, but also art, philosophy, and all aspects of human creativity, inviting us to rethink the cosmos and our place within it. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folklore, the moon hides secrets that have eluded us for centuries. Among these mysterious features is the lunar South Pole, a region shrouded in perpetual shadow and intense cold, untouched by any previous lunar mission. This is the story of India's Chandrayaan-3 in unknown territory. Launched on a journey of more than 238,000 miles, Chandrayaan-3 embarked on a mission not only of distance, but also of discovery. Its goal was to unravel the mysteries of the lunar South Pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that one must traverse a maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its main objective was clear, but difficult to achieve: a soft landing near the moon's south pole, a feat that had never been achieved before. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the vacuum of space, overcoming the challenges of insertion into lunar orbit and descent. The south pole of the moon is a landscape unlike any other. Here, the terrain is a mosaic of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to do so safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, the descent began. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the moon. Imagine a spacecraft autonomously navigating a maze of craters and rocks in search of terrain safe enough for landing. The landing module's onboard systems worked tirelessly, analyzing every inch of the terrain below. Facing this treacherous landscape, the landing module also struggled against extreme temperatures. The south pole of the moon is a place of extreme contrasts. The sun barely rises above the horizon, and the shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat faster. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a slight bump, Vikram landed, marking a historic moment not only for India, but for lunar exploration in general. In the silence of the lunar south pole, Chandrayaan-3 began its mission of exploration and discovery. Thus, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The mission's objective was to maximize the study of the moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, it is so rarefied that it almost resembles a vacuum. Chandrayaan-3's instruments, developed with the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delves into the lunar ionosphere. This layer, formed by solar energy that ionizes the atoms of the exosphere, plays a crucial role in lunar communications and navigation. Chandrayaan-3's measurements were designed to provide unprecedented information about the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was the study of temperature variations just below the lunar surface using one of the landing module's 4 instruments, the CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, submerged in the lunar regolith, had the critical mission of mapping the thermal profile of the lunar soil. Chandrayaan-3's results revealed a strong contrast in surface temperatures during a lunar day. Temperatures rose dramatically to 60 degrees Celsius. While at only 8 centimeters deep, they dropped significantly to minus 10 degrees Celsius, demonstrating that the lunar soil is a potential thermal insulator. This discovery opened up new opportunities for future lunar habitats, as it suggests that the lunar regolith could serve as a thermal insulator to protect astronauts from the moon's harsh temperatures and harmful radiation. These studies were more than just scientific endeavors. They were steps towards a future in which the moon could be a gateway to further space exploration. The mission's results on the exosphere, ionosphere, and lunar subsurface temperature laid the foundation for understanding the moon's environment and its potential to support human life. In the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed in more than 50 years, a moonquake. The mission managed to shed light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument designed to detect the slightest tremors on the moon, achieved this. Chandrayaan-3 detected what seemed like a lunar earthquake, a significant discovery, given that the last observation of this type was made during the Apollo missions in the early 1970s. Lunar earthquakes are fundamentally different from terrestrial ones. The seismic activity of the Earth is largely due to the movement of tectonic plates. The Moon, which lacks these plates, experiences earthquakes for various reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a matter of scientific interest. The data from Chandrayaan-3 suggests several possible causes for these quakes. One theory is the collision with meteorites, which could cause shock waves that penetrate the lunar crust. Another is the gravitational attraction of the Earth, which causes tidal forces that load the lunar crust. Finally, extreme temperature fluctuations on the lunar surface can cause expansions and contractions that lead to earthquakes. These earthquakes are not only superficial phenomena, but windows into the interior of the Moon. By analyzing seismic waves, scientists can deduce the composition and structure of the interior of our satellite, which resembles an ultrasound of the lunar interior. This information is of great importance to understanding the formation and evolution of the Moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened new perspectives on the geological processes that shape the Moon to unravel the geological mysteries of the Moon. Chandrayaan-3 carried out another exploration. Among the most intriguing findings is the discovery of sulfur, an element whose presence on the Moon has been shrouded in mystery. The laser-induced breakdown spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes small samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thus revealing the presence of various elements, including sulfur. Sulfur on the Moon is a significant finding. On Earth, sulfur is often associated with volcanic activity, which raises questions about similar processes on the Moon in the past. Its presence could provide information about the volcanic history of the Moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that has intrigued scientists for decades. Water ice on the Moon is not only a scientific curiosity, but also a potential resource for future human missions, as it provides water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, did not find direct evidence of water ice on the lunar surface. However, the lack of direct evidence is not a conclusion, but a clue that leads to new hypotheses. One theory is that of the carbon trap, in which water vapor can migrate to permanently shadowed craters of the poles and freeze into ice. The detection of sulfur adds another layer to this theory, since sulfur can be trapped with water ice and released as a result of the decomposition of water molecules by high-energy solar radiation. The lack of direct evidence of the existence of water ice raises important questions. Is the ice located deeper below the surface, protected from detection by the insulating properties of the lunar soil, or is its prevalence more heterogeneous and difficult to detect than previously thought? During its exploration of the south pole of the Moon, the Chandrayaan-3 found something more than sulfur. The LIBS instrument of the rover carried out the first in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each of which reflects part of the complex geological history of the lunar surface. Other measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues about the formation of the Moon and its evolutionary history. Studies focused on the presence of hydrogen, a key component in the search for water. The discovery of these elements and the mission's continued search for water ice underscore the dynamic and complex nature of lunar geology. Each discovery and each unanswered question brings us closer to our goal of understanding our closest celestial neighbor and prepares us for the next steps in lunar exploration. Each discovery, each unanswered question, brings us closer to our goal of understanding our closest celestial neighbor and prepares us for the next steps in lunar exploration. The Chandrayaan-3 mission to the south pole of the moon opened a new chapter in lunar exploration and also paved the way for the next ambitious leap, the LUPEX Lunar Polar Exploration Mission, for its acronym in English. This joint initiative between the Indian Space Research Organization and the Japan Aerospace Exploration Agency is scheduled for 2026 at the earliest. LUPEX plans to send an unmanned lunar lander and a rover to continue exploring the South Pole region of the moon. JAXA will likely provide the H-3 launch vehicle and the rover, currently under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation in lunar exploration. Its objectives are multiple. It will demonstrate new surface exploration technologies, fundamental for sustained lunar exploration in the polar regions. Precise landings will be achieved through the use of a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander to investigate the lunar mission. The LUPEX rover will carry several instruments from JAXA and the ISRO, including a drill capable of collecting samples at a depth of 15 meters. 15 m. The search and analysis of water are key objectives of the mission, and the possible discovery of water ice could be a turning point for future lunar missions. In parallel to LUPEX, the ISRO is planning the Chandrayaan-4 mission designed to bring samples from the moon, which is scheduled to launch in 2028. Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a reentry module. The ambitious goal of the planned mission is to bring soil samples from the moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers such as sample collection, docking in lunar orbit, and the return of the samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the moon's mysterious nature. These results provide crucial information about the geology of the moon, its internal structure, and the potential for future lunar habitats. Looking ahead, lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, based on the legacy of previous ones, will continue exploring the mysteries of the moon. The role in these efforts is not only that of a participant, but also that of a pioneer. These events inspire us to look beyond the infinite mysteries of the cosmos. The solar system has served as a reliable place for life, but someday humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately searching the dark depths of space for a refuge for life. So far, none of the exoplanets that we have found refutes the hypothesis of life singularity. But what if we were simply looking in the wrong place? Perhaps it is not the planets that hold all the answers, but their moons in the mystical deep space. Exomoons are different from any other satellite in our solar system. The size of our Earth, these hidden giants have an amazing characteristic. Life can be found inside them many more times than in normal exoplanets. Today we will immerse ourselves in the mysterious and distant universe and try to discover why exomoons could someday change humanity. Let's go back to the beginning of the history of exoplanet science, since astronomy received a strong boost only in the mid-20th century. Scientists began studying the first exoplanets not long ago. The first confirmed exoplanets were recorded in 1992. It was a group of planets with mass similar to that of Earth that orbited around the pulsar PSR B257+2. Only 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, dedicated to the study of planetary systems outside our solar system, and, in addition, to the search for places where life similar to human life could originate. We did not have to wait long to find other exoplanets in our visible universe. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years, they had to wait a long time. In the following years, astronomers found several more exoplanets, until in 2009 the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets with size and conditions similar to those of Earth. Currently, we already know more than 5,500 planets outside the solar system, and the James Webb Telescope, recently sent, will probably show us even more distant planets. In addition, in 2013, scientists were able to determine the color of the planet, and a year later they were able to record its magnetic field and, subsequently, volcanic activity. Finally, in 2018, astronomers made a new potentially revolutionary discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. Although at first glance, this may not seem like such an incredible discovery, exomoons open a new chapter in modern astronomy, not only because they are novel and hitherto unexplored space objects, but also because they are potential elements to sustain life on exoplanets and on the satellites themselves. Each year, the knowledge about distant and faint exoplanets deepens, which brings scientists closer to a complete picture of the history of the entire universe. But how did scientists manage to confirm so many planets in such a short time, when it is impossible to take a picture of each one? Only 69 planets have been found with images. The most used method is the transit method, which you may already know. When an exoplanet passes in front of its central star, it becomes slightly fainter, which reveals the presence of an object orbiting around it. Although this method does not allow us to directly observe the planet and may turn out to be just an error, it is currently the most effective of all. The exploration of exoplanets plays a crucial role in all of astronomy and in the future of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are not of great interest for current research. The main problem associated with the search for these exoplanets is the difficulty in detecting them by telescope radars. Although no scientist denies that some exoplanets may have satellites, it is an extremely difficult task and, to some extent, even impossible for our current technologies. The transit method, or more precisely the method of studying the displacement of the spectrum of stars, can confirm the existence of an exoplanet, but not that of a satellite that orbits around it, except in very exceptional circumstances, such as, for example, that the spacecraft is in the closest possible proximity to the object of observation, due to a completely insignificant change in the brightness of the star. Therefore, even the first exomoon found by Kepler, and those discovered later near the planets Kepler 1708b and Kepler 1513b, are still not considered conclusive proof of their existence, and, therefore, there is the possibility that it is simply some kind of technical error during the observation, which is not so far-fetched, since subsequent observations have not yielded encouraging results. However, as in the case of the giant satellite Kepler 1625b, an exomoon can be seen if it is large enough. So, until now, the first hypothetical exomoon could be the size of Earth in a strange inclined orbit like that of Triton, the moon of Neptune. The enormous size of a possible moon could become one of the most important elements in the search for other moons. So currently more than 20 exomoon candidates are known, all of them gigantic, at least in the case of Kepler 1625b, the star around which it orbits, which is a red giant. This dying star can heat the atmosphere of the moon, increasing its effective diameter and allowing scientists to detect satellites more frequently. However, perhaps at this time, exomoons do not have too much scientific importance for scientists to invest many resources in developing technologies to find them at this stage of our science. Exomoons do not seem to have a higher priority than other space objects, such as exoplanets. The exomoons of distant planets are too complex to study and have many possibilities of giving false positive results. So it may take months or even years of observation and analysis to confirm the existence of a satellite, when it seems more rational to dedicate those resources to exploring a planet with the potential to harbor life, including human life. Of course, it is possible that the exomoons hide life inside, but the alternatives in the form of rocky exoplanets like Earth are still much more important in scientific circles. But let's focus on the exomoons themselves and try to investigate them. Is it really necessary to study these mysterious and hidden moons? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, though not in the near future. The first thing that catches the attention of scientists, even of simple exomoon candidates, is their size. The largest moon in the solar system, Ganymede, which orbits around Jupiter, has a diameter of 3,273 miles or 5,268 kilometers. But the recorded exomoons can reach the size of Earth or even Neptune. Therefore, since these moons are even difficult to distinguish from exoplanets, it is incredibly exciting to imagine what they could be like and what activity they could present. It is possible that some large exomoons have many of the characteristics of planets, and that their study could change everything we know about satellites. Their similarities with other exoplanets, such as their probable geological activity, lead us to the next important point for careful study in the future: the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could hypothetically be a refuge for living organisms due to the presence of global oceans. However, what about the much more massive moons that not only can support a dense atmosphere, but also have more access to the chemical elements necessary for the formation of life, both from the inside and outside? According to a study from the University of Washington, exomoons have more potential to harbor life than exoplanets, since they also have a habitable zone, although it is slightly different. The main argument in favor of exomoons as one of the most intriguing places for the existence of life is the availability of various sources of heat. The first source is the star itself, and the second is its planet. The moons are heated by the planet's gravitational attraction, which maintains the probable water inside the moon in a liquid state. In addition, the heat from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bring diverse crucial chemical elements to the surface. So exomoons are not as simple as they seem. Perhaps the difficulty of finding them will be rewarded with a potential scientific advance. Finally, exomoons can become the necessary tool to study the formation of our universe. So the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for sustaining life, and what is the history of other planetary systems in general. In particular, comparing the moons of the solar system with those of distant systems can provide scientists with an understanding of the particularities and conditions of their development, as well as an approximate value for the abundance of systems in which complex intelligent life has developed. Earth, hypothetically, could be almost the only planet where life could have formed, at least in the visible universe. And any clue about exomoons with potentially greater possibilities of harboring living organisms could confirm or refute this hypothesis. However, for now, the in-depth exploration of exomoons is only a matter for the future. On the other hand, the mission of the James Webb Space Telescope will continue for several more years, so perhaps the hope of finding an exomoon for the first time this decade will not disappear. However, given that the search for exomoons is an extremely difficult and almost impossible task for our current technologies, it is likely that exomoons will become one of the engines of technological progress, since we know that the transit method or the gravitational lens will not help to look for microsignals of the presence of exomoons. So this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects, but this is a task for the near future. In the long term, both the intriguing moons and the exoplanets will require a much more exhaustive analysis, including the use of images and samples of the atmosphere or even the soil. So if interesting candidates are ever found where extraterrestrial life exists, it is likely that exhaustive space missions will be carried out that advance the investigation. The only step we have left to take is to find an exoplanet or exomoon by 2026. The European Space Agency plans to send the Plato mission, which will continuously observe several areas of outer space to capture objects during transit. The mission will last 6 years, and it is possible that exoplanet or exomoon. In 2026, the European Space Agency plans to send the Platon mission, which will continuously observe several areas of outer space to capture objects in transit. The mission will last 6 years and could be the one that achieves this expected discovery. However, the benefits of the search and exploration of exomoons are not limited to technological advance. Exomoons are valuable natural laboratories located near various planets and stars, and the analysis of the impact of these bodies on the moons will not only deepen what is known about the formation of the planets, but will also demonstrate to scientists the variety of conditions in which life can develop. For example, traces of biomes or even the technological footprints created by civilizations on various moons can provide a clear picture of the indications of the development of intelligent life, which would allow establishing more priority routes for future missions to the planets or moons with the most probabilities of harboring extraterrestrial life. But for now, we can only wait for the moment when we find the first exomoon and begin a long but transformative journey that will change life. Exomoons, despite their invisibility and skeptical insignificance, can one day crucially change everything that the human race knows about our vast universe. Even a small observation can end up becoming the main engine for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome and mysterious cosmos one day cease to be so confusing for us. But in the face of the immensity of the universe, we must never lose our enthusiasm for learning, no matter how difficult or distant our goal may be. Music, Saturn has captivated the human imagination, from ancient civilizations to modern astronomers. The Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How the mystery deepens. Saturn has long been a symbol of the unknown and the mysterious. Its iconic rings have been the object of amazement and speculation since Galileo's time. But what if we told you that these rings, as eternal as they seem, are actually a fleeting cosmic phenomenon that adds to the intrigue? A storm twice as wide as Earth with a mysterious hexagonal shape that breaks out at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries do not just end there. Saturn's satellites, Titan and Enceladus, offer conditions that could harbor life. Lakes of liquid methane and geysers that launch water and organic matter into space make these satellites more than just celestial bodies. They are possible homes for life. Join us to learn more about this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw left him perplexed: a planet with something like ears. He did not realize that he was seeing the edges of Saturn's magnificent rings, a characteristic that would baffle astronomers for centuries. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 when Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Entering the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly by Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were previously inaccessible to terrestrial telescopes. But it was the Cassini mission that really revealed Saturn in all its splendor. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites, from the discovery of columns of water ice on Enceladus to the capture of the ethereal beauty of a hexagonal storm at Saturn's North Pole. Cassini revolutionized our understanding of this distant world, and here is an interesting fact. Long before the arrival of telescopes, the Maori of New Zealand had myths that described Saturn with a pararo or belt around it. How they knew it remains a matter of debate and speculation. But, as we will see later, Saturn hides more than one mystery. What do you think could have created a hexagonal storm with a surface larger than Earth? Saturn is home to a geometric enigma at its North Pole. a six-sided storm that has baffled scientists for decades. This six-sided wonder is not just a superficial characteristic, but a deep and lasting mystery that defies knowledge about fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft, but it was not until the Cassini mission, which orbited Saturn from 2004 to 2017, that we were able to see this cosmic spectacle in the front row. The high-resolution images from Cassini showed a symmetrical jet stream surrounding the hurricane-like vortex at the hexagon's center. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what causes this hexagonal storm? Researchers at the University of Harvard have developed a 3D model that suggests that deep thermal convection in the outer layers of Saturn could be to blame. This model shows that the storm could extend thousands of kilometers into the depths of Saturn's atmosphere, far beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in laboratory settings. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they offer a glimpse into extraterrestrial phenomena. This contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of gas giants from the planets of the terrestrial group. The hexagon's longevity is another mystery. It has been observed for at least 4 decades, and possibly much longer. This constant characteristic suggests that whatever feeds the hexagon is not a temporary phenomenon, but a stable, perhaps permanent, aspect of Saturn's internal dynamics. Let us now turn our attention from the mystery of the hexagon to another wonder of Saturn. Its rings are more than just a celestial jewel. They are dynamic systems in constant change that interest both astronomers and the public. But what are these rings made of, and why are they so ephemeral? Saturn's rings are mainly composed of water ice, with a mixture of dust and rocky material. Their size varies from tiny particles to huge chunks the size of houses. These ice particles are not static. They are in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with unique characteristics. The most notable are the A, B, and C rings, separated by gaps, such as the Cassini division, a 3,000-mile gap between the A and B rings. The origin of Saturn's rings has been a subject of debate. One popular theory suggests that they formed from the remains of a shattered moon. Another theory claims that they are the remains of material from the solar system's formation, captured by Saturn's gravity. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on dust contamination rates. Saturn's rings do not last forever, but are slowly disappearing due to a phenomenon known as ring rain, in which particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeorite bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could vanish in 100 million years. The disappearance of the rings would not only change Saturn's appearance, but could also have consequences. The rings of Saturn could disappear in 100 million years. The disappearance of the rings would not only change the appearance of Saturn, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to vanish in the annals of eternity. Saturn, the ring giant of our solar system, is not only a celestial wonder, but also a cosmic playground containing some of the most intriguing satellites. 2 of these, Titan and Enceladus, have fascinated scientists and sparked debate about the possibility of life beyond Earth. Titan is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what is truly surprising is the speed at which Titan moves away from Saturn, 100 times faster than previously thought, an astonishing 43 centimeters per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect the internal dynamics of Titan and perhaps even its potential for the existence of life? An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Titan a tempting target in the search for extraterrestrial life. But the question remains, what would life be like in an environment so radically different from Earth? And let's remember Enceladus, another satellite of Saturn, very different from Titan. It is an icy world with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an oceanic world to a new level. Not only does it have an underground ocean, but it also expels it into space, where a space probe can collect samples. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water gushing from hydrothermal vents. Hydrothermal vents can provide the conditions necessary for life as we know it on Earth. On Earth, these vents teem with life forms that thrive in extreme conditions. Could Enceladus vents harbor similar, but alien, life forms? Enceladus also contributes to Saturn's E-ring, a unique feature that further enriches the dynamic relationship between the Moon and its host planet. The icy particles of this ring open a window into the internal chemistry of the Moon, providing clues that could reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but with very different characteristics. Both present compelling arguments for the possibility of life, fueling our curiosity as we contemplate the possibilities on Saturn satellites. It is worth noting that our curiosity is not limited to telescopes and computer models. The next missions aim to study these places closely and perhaps answer our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan, with a launch scheduled for the 2030s. This helicopter will fly over Titan's varied terrain, from dunes to impact craters. The main objective of Dragonfly is to search for the basic components of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing data on Titan's chemistry. Equipped with a set of scientific instruments, Dragonfly seeks to understand the Moon's geological processes and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although there are no planned missions to Enceladus currently, the Moon's potential for life has made it an ideal candidate for future exploration. Scientists are proposing missions that could fly through Enceladus' plumes and take samples directly from its underground ocean. Such a mission could analyze the plume's chemistry for signs of life or prebiotic chemistry. The presence of hydrothermal vents in the oceans of Enceladus adds another layer of intrigue, suggesting an environment in which life could thrive despite the technical challenges. A mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence of extraterrestrial life, or at least clues about the conditions necessary for life, music, to exist. As we have mentioned, Saturn's rings are not eternal, as was once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade. But how important is this for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, mainly water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. The ring rain is not just a trickle, but a torrent that drags water in amounts equivalent to an Olympic swimming pool every half hour. The mystery is compounded by the relative youth of Saturn's rings, since, although Saturn is about 4,600 million years old, data from NASA's Cassini mission suggests the rings could be only a few hundred million years old. This leads us to wonder if Saturn's rings are so young. What catastrophic event could have led to their formation? Was it the destruction of a moon, or perhaps the capture of a passing comet? Cassini's space dust analyzer has added another layer of complexity. For 13 years, it has collected 163 dust particles from outside the Saturn system. Surprisingly, The rings turned out to be quite clean, suggesting that they have not existed long enough to accumulate an excess of cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. As if the rings were in a cosmic laboratory or in a clean room, isolated from the dust that permeates the rest of the solar system. As the rings disappear, Saturn's appearance will undergo a dramatic transformation. These rings have been a mark of the planet. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making it a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to that of its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like companions in a cosmic dance, each affecting the other in subtle yet significant ways. As we continue to study these celestial bodies, we can state that the fate of one can shed light on the mysteries of the other. Our universe hides a mystery that has long captivated the human mind, a question that bridges the known and the unknown, the simple and the complex. Here, on Earth, life thrives in a continuous movement of order and chaos. Each life form is evidence of a hidden order, a pattern woven into the very fabric of existence, from the smallest microorganisms to the largest mammals. But what if the complexity of life, the very essence of our existence, could be explained through a mathematical framework, not only through the lens of biology? This is the territory of assembly theory, a revolutionary concept that transcends traditional science. It is a journey into a world where mathematics and biology converge to reveal the hidden architecture of life. Let's imagine a universe in which the secrets of life, from the simplest molecule to the most complex organism, are encoded in mathematical language and waiting to be decoded, where the line between the living and the inert blurs, giving rise to new possibilities and understandings. Let's explore how this revolutionary idea is changing our perception of life, evolution, and the cosmos itself. And perhaps we can even get closer to answering the fundamental question: what is the true nature of life in the universe? Since the dawn of civilization, mathematics has been a language of the universe, the tool to decipher the mysteries of nature. But how does this language of numbers and equations relate to understanding the very essence of life at its core? Assembly theory offers a simple but profound idea. The complexity of life can be measured and understood through a mathematical prism. Let's think of life as a puzzle in which each piece represents a molecular block. Assembly theory seeks to show how these pieces come together step by step to form the complex structures that define living organisms. Each step in this assembly process represents a leap in complexity, from simple atoms to complex proteins. The theory introduces the concept of the assembly index, the cornerstone of this theory, which measures the number of steps needed to build a biological structure. It is a numerical value that captures the essence of complexity by quantifying the immeasurable. But how does the standard model of physics fit within this? The standard model of physics describes the fundamental particles and forces that govern our universe. It seems completely separate from biological complexities. However, assembly theory bridges these fields. In assembly theory, the standard model lays the foundation for understanding forces and interactions. It is a bridge between the microscopic world of quarks and leptons and the macroscopic world of living things. Another important element of the theory is the concept of studying dynamic systems, phase space. This is a mathematical concept used to describe all possible states of a system in assembly theory. The phase space allows us to trace the path of the assembly of life from a single point that represents the simplest form of life. A space expands, branching into almost infinite possibilities. Each path represents a different route life can take in this unlimited mathematical landscape. The trajectories of evolution and its complexities unfold in this mathematical framework, offering us a new perspective on life's complexity. It is not only about the particles and forces described by the Standard Model, but about how these elements combine and interact over time to create the diverse patterns of life we see. This is where the chaos of random molecular interactions gives way to the order of living structures. So let us ask ourselves, are the complexities of life simply a product of chance, or is there a deeper cause? Let us consider two very contrasting concepts: complexity and entropy. Entropy, a measure of disorder and randomness, seems to contradict the complexity that we observe in life. How do these opposing forces coexist in nature? This is where assembly theory offers a revolutionary perspective. A central element of assembly theory is the assembly index, a tool designed to measure life's complexity. Think of it as a cosmic rule that measures the steps needed to assemble a biological structure from its simplest parts. Imagine a single molecule as the starting point on this scale. As you ascend the scale, each step represents a more complex assembly, from molecules to cells and onward. The higher the index, the greater the complexity, and the less likely it is that the structure arose by chance. Now let us delve into the interaction between entropy and delve into the interaction between entropy and complexity. Entropy, a concept rooted in thermodynamics, suggests that systems tend naturally to disorder. However, life defies this trend, evolving from simple origins to a variety of forms combined in the complex, ordered structures we see today. How does assembly theory resolve this apparent contradiction? It suggests that life is inherently a process of overcoming entropy. Through the assembly index, we see that life's complexity is not a challenge to entropy, but a journey through it. Let us consider the early Earth, a primordial soup of simple molecules. Over millennia, driven by the laws of physics and chemistry, these molecules began assembling into more complex structures. Each step along the way marked a victory over entropy, a step toward greater complexity in life. By rethinking evolution through assembly theory, we see it not as a mere biological process, but as a mathematical inevitability. The emergence and evolution of life became a story of increasing complexity, a story written in the language of mathematics. Let us now move on to a trivial question, but one that is presented in a new light. Are we alone? The search for extraterrestrial life has captivated our imagination for centuries. Now, thanks to assembly theory, we have a new tool for this cosmic search. Assembly theory offers a unique approach to detecting extraterrestrial life. It is not about scanning the sky for radio signals or analyzing light spectra for oxygen, but about understanding the complexity of molecules and structures that may indicate life. Let us imagine that we scan the atmosphere of a distant exoplanet or the surface of a moon in our solar system. Using assembly theory, we could analyze the molecular complexity of the samples for patterns indicating the presence of life. The higher the assembly index, the more likely it is that these molecules are the result of life and not random processes. However, the path to discovering extraterrestrial life is full of challenges and limitations. One of the biggest obstacles is our understanding of life itself. Our definition of life is based on what we know about life on Earth. What if it does not meet our biochemical standards? Another problem is the immensity of space. The universe is vast, and our ability to explore it is limited by current technology. Even with the most sophisticated telescopes and probes, we can analyze only a small fraction of the cosmos. Furthermore, the assembly theory, while powerful, is still in its beginnings. A new approach and its application to the search for extraterrestrial life is an unexplored area. There are doubts about its applicability and precision in different environments, especially those very different from terrestrial ones. Despite these problems, the potential of assembly theory in the search for extraterrestrial life is enormous. It could redefine our understanding of life in the universe and unlock new doors in astrobiology. Thus, assembly theory offers a new way of seeing life, not only as a biological phenomenon, but as an emergent property of cosmic complexity. Let's imagine the early days of our planet, a world in movement, a melting pot for the chemistry of life. Here, in this chaotic environment, simple molecules began their assembly journey, a process governed by the laws of physics and chemistry, but that leads to something much deeper: life. According to assembly theory, life arises when these molecular structures reach a level of complexity that allows them to store and reproduce information. This is where chemical memory comes into play, a crucial step for the evolution of life. Chemical memory is the ability of certain molecular structures to retain their structure. In other words, we can say that it is the blueprint of life in assembly theory. This is where reproducibility becomes key. The ability to reproduce these patterns, to transmit them from generation to generation, is what drives the evolution of life, from the simplest RNA molecules in the primordial soup to the vast diversity of life we see today. Each step in this evolutionary journey has been a step forward in the assembly index. Each increase in complexity represents a triumph over the entropy that governs the universe. But the story of the origin and evolution of life is not just a story of increasing complexity. It's also a story of resilience and adaptability. Life has found a way to thrive in the most extreme environments, from the ocean depths to the confines of space. In the field of scientific discovery, each new theory is analyzed and debated. Assembly theory, a concept that promises to revolutionize our understanding of life and complexity, is now at a crossroads, questioned by critical voices such as Dr. Hector Zenel. The criticism presented by Zenel raises fundamental questions about the future evolution of assembly theory, which encompasses an impressive 18,000 words. The article requires time and reflection, and its dedicated reading can take between 1 and 2 hours. It is not a superficial review of the subject, but a deep immersion into the heart of scientific debate. For those who are interested, we leave a link in the description to both articles, the study and the counterarguments. Looking ahead, the role of assembly theory in scientific research remains uncertain. Will it adapt and overcome these challenges, or will it remain a footnote in the history of science? Despite the disagreements, one thing is clear. The debates surrounding assembly theory have started a conversation about the nature of scientific discovery. These debates emphasize the need for transparency, rigor, and humility in the pursuit of knowledge. In the end, the impact of assembly theory on future research may not lie in its specific claims, but in the lessons it teaches us about the scientific process. As we explore the mysteries of life in the universe, these theories will come and go. But the search for understanding, the search to unravel the mysteries of our existence, will always remain the focus of scientific research. Let's imagine a single point, a simple speck of light floating in an infinite sea of darkness. It is not just a random point, it is our home, Earth. But what if we told you that this point is just a fleeting moment in a cosmic landscape so vast and complex that it defies human understanding? Imagine a night sky adorned with stars, each of which represents a sun, many of which have their own planets. Now multiply that image by 100 billion. Even in this case, we would have barely scratched the surface. Beyond our Earth, beyond our sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is in itself a wonder, struggles to comprehend this scale. Our brains are designed to understand the elevations and slopes of mountains and the immensity of oceans. But how can we understand a structure that extends billions of light years? Today, on a journey to explore these galactic threads, the breasts and muscles of the universe itself, we will delve into an almost incomprehensible realm, where even the speed of light seems slow. Spiders weave intricate webs, fine but resistant, each thread connected to the other in a complex pattern. The architects of nature create these fabrics to survive, capture prey, and probe the environment. Now imagine a fabric woven not by spiders, but by the very fabric of space and time, a fabric that connects galaxies, star clusters, and dark matter in a complex network. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound together by gravity. But what gives this network its structure? The answer lies in something we cannot even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this network is built. Although it is invisible, we cannot even see dark matter. Scientists believe that dark matter constitutes about 27% of the universe and acts as the framework on which this network is built. Although it is invisible, its presence is perceived through the gravitational force that determines the formation of galaxies and the trajectories they follow. The cosmic web has not always been as we see it today, but has evolved over billions of years from small density fluctuations in the early universe. These fluctuations grew, drawn by gravity, and ended up forming the majestic filaments and nodes we see now. One of the most impressive examples of a galactic filament is the Great Wall of Hercules in the Northern Crown. This colossal structure extends along 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just academic. It is a search to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution, or is there a grander design in progress? Scientists use a variety of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread in a story that encompasses the entire universe. Here is Earth, a blue and green pearl suspended in the immensity of space, a planet replete with life, from the microscopic to the magnificent. It is easy to think of Earth as the center of everything, but in the grand scheme of the universe, it is just a speck in our solar system. Earth is just one of the 8 planets that orbit the Sun, yet stands out for its unique capacity to harbor life. The oceans, the atmosphere, the magnetic field. All these elements exist in a delicate balance. If we move the image even further away, our entire solar system becomes a small point in one of the spiral arms of the Milky Way, a galaxy that houses hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, it is just one galaxy in a cosmic network of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our own galaxy, Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment that surrounds the Earth. However, despite its apparent insignificance in the cosmos, Earth is unusual for one reason: it has life. It is the only known celestial body where life not only originated, but has evolved to reach an incredible level of diversity and complexity. The search of humanity to understand its place in the universe has given rise to remarkable scientific advances. The telescopes observe the most remote corners of the universe, and the supercomputers simulate the cosmic network, which helps to answer fundamental questions about the nature of reality. For example, look at the Sun, the ball of burning plasma that illuminates our sky and heats our planet. It is the reason you can see these images, the reason life exists on Earth. But in the context of the cosmic web, the Sun is just a node, a solitary star among countless others. Near the Sun, we find other stars, some smaller and colder, others larger and hotter. Each of these stars is like a bead on an enormous cosmic thread, joined to each other by gravity and dark matter. Our Sun is in the Orion arm of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is nothing special, just one of the approximately 400 billion stars in the great expanse of the cosmic web. Stars like our Sun form complex nodes that connect larger structures, such as galaxies and clusters of galaxies. They are the building blocks, the fundamental units that shape the network. So, what fuels this celestial beacon? The answer is nuclear fusion. In the depths of the Sun, hydrogen atoms collide and fuse to form helium, releasing enormous amounts of energy. This energy not only fuels the Sun, but also balances the gravitational forces that try to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life, drives our climatic systems, feeds photosynthesis, and even influences the climate of the Earth in the long term. Understanding the Sun is fundamental to understanding the cosmic web. Several missions have been launched, such as the Parker Solar Probe and the Solar Dynamics Observatory, to study the Sun's behavior. These missions provide information about the solar cycles, the magnetic fields, and even the Sun's future. Although the Sun is a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it is just one example in a universe replete with stellar diversity. Each star, regardless of its size or lifespan, plays a role in the configuration of the cosmic network. From the smallest red dwarfs to the massive blue giants, each star is a unique knot that contributes to the overall structure of the galactic filaments. Stars are often classified by their mass and brightness and represented in a graph known as the Hertzsprung-Russell diagram. This diagram shows a star stage of life and gives clues about its future destiny. Let's take, for example, a red dwarf, the most common type of star in the universe. They are small, cold stars, also called M-type stars, which usually have less than half the mass of our Sun. They compensate for their small size with their longevity, since they burn for tens or hundreds of billions of years. Red dwarfs are frugal, since they convert hydrogen into helium much more slowly than larger stars do. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare them with O-type stars, the rare titans of the stellar world. These stars are over 15 times more massive than the Sun and can be 1,000,000 times brighter, but they live fast. O-type stars usually have a short and spectacular life, which ends in supernova explosions. O-type stars end their lives dramatically. They collapse under their own gravity and then explode as supernovas. These explosions scatter elements such as carbon, oxygen, and iron into space, which favors the formation of new stars and planets. Star clusters are like cosmic nurseries, places where different types of stars are born. These clusters serve as nodes in the cosmic network, connecting different regions of the galaxy and even galaxies to each other through filaments. Computer simulations help astronomers understand how different star types contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in weeks, showing how stars serve as building blocks of larger cosmic structures. Thus, we have already discovered that stars are not eternal. They are born, live, and then die. The life cycle of a star is a cosmic journey that spans billions of years, playing a key role in the evolution of the universe and the structure of the cosmic network. The birth of a star is a spectacle of cosmic scale. It begins in a nebula, a vast cloud of gas and dust. Gravity attracts these particles, which become denser and hotter until nuclear fusion ignites a new star. Once a star reaches the main sequence phase, it enters a period of stability. The hydrogen in the core is converted into helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, where our Sun is now. But even stars like ours must face changes. In about 5 billion years, the Sun will run out of hydrogen. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the star's final destiny. Depending on its mass, a star will have one of several endings. Stars with less mass, like our Sun, will lose their outer layers, leaving behind a white dwarf. More massive stars can undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The agony of stars scatters important elements through space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of cosmic creation and destruction. The cosmic network, from individual stars to entire galaxies, is a complex network of interconnected structures. But what connects these galaxies? What are the threads that weave the universe's complex fabric? The answer lies in the galaxy clusters. Galaxy clusters are huge groupings of galaxies bound together by gravitational force. They can contain only a few or thousands of galaxies and often extend over millions of light years. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galaxy clusters, even though we cannot see it. Though we cannot see it, we know it exists, as it holds the cluster together and shapes its overall structure. Within a cluster, galaxies are not static but in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge under the influence of complex gravitational interactions. Sometimes, these interactions can lead to dramatic events, such as galaxy collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial for the evolution of galaxy clusters and, by extension, of the cosmic network. But clusters are not the end of the story, as they often group together to form superclusters, among the largest known structures in the universe. These superclusters serve as main nodes of the cosmic network, connecting numerous clusters and filaments. Understanding galaxy clusters is key to unlocking the mysteries of the cosmic network, as they serve as threads connecting galaxies, forming the paths through which matter and energy flow on a cosmic scale. After studying the colossal structures of galaxy clusters, the threads that weave the cosmic network, we now turn our attention to an even more mysterious phenomenon. What if there were real threads, chains of pure energy, binding the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the universe's loose threads, remnants of the earliest moments after the Big Bang. Let's imagine the universe moments after the Big Bang, in a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not all went well. In some regions, there were twists that led to the formation of cosmic strings. Cosmic strings, if they existed, would be incredibly thin but dense. A string less than an inch wide could weigh as much as Earth. They would extend across the vast expanse of the universe, perhaps even from one end to the other. Due to their enormous mass, cosmic strings would exert a strong gravitational attraction, affecting the movement of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues on. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the string's existence is confirmed, they could become the missing links that help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to the structures of incommensurable scale, the superclusters. They are gravitational anchors that hold together vast networks of galaxies and clusters. Let's imagine that we move away from our galaxy, the Milky Way, beyond our local group of galaxies, and even beyond our local Virgo supergroup. We would find a network of superclusters, each containing hundreds to thousands of individual galaxies united in a complex dance of gravity. The superclusters are unevenly distributed and form a kind of cosmic skeleton around which the galaxies and clusters of galaxies are located. This skeleton gives the cosmic network the shape that defines the universe's large-scale structure. Within the superclusters, the galaxies and clusters are in constant motion under the influence of the collective gravitational attraction of the entire structure. This dynamic flow of matter and energy keeps the cosmic network alive and constantly changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies, like the Great Attractor. These are regions with such strong gravitational force that they influence the movement of the entire supercluster, acting as axes of a cosmic network. Understanding superclusters is fundamental to cosmology, as they are the largest objects for studying the expansion of the universe, the distribution of dark matter, and even dark energy's mysterious force. Scientists estimate that the observable universe contains 2 trillion galaxies, yet what we can see represents less than 5% of the universe. At the edge of the precipice of cosmic knowledge, we feel humbled by the scale and complexity of the universe. From the smallest to the observable universe is estimated by scientists at 2 trillion galaxies, and yet what we can see represents less than 5% of the terrestrial universe. At the edge of cosmic knowledge, we feel humbled by the scale and complexity of the universe, from the smallest particles to the largest galactic filaments. Each element is a piece of the puzzle. Here we are, a pale blue dot, a simple speck in the cosmic network. But it is from this point of view that we begin to unravel the deepest mysteries of the universe. Armed with telescopes capable of seeing billions of light years away, we become not only spectators, but active participants in this cosmic journey, and each new discovery is a step towards answering the eternal question that leads us all to reflect. What other mysteries does the universe hide that we have not yet unraveled? Imagine a universe that has just begun, only a few 100 million years old, an era in which the first galaxies were forming. Thanks to the James Webb Space Telescope, we have made revolutionary discoveries that transport us to an ancient era, before the universe existed, where every little point of light is a galaxy, a vast cluster of stars, planets, and mysteries. Among these countless galaxies, some are so far away that their light has taken billions of years to reach us. Studying these distant galaxies is of great importance because it helps us understand the early stages of cosmic evolution and the formation of structures. This spring, astronomers using the JWST were able to observe the early universe and discovered galaxies that existed more than 13 billion years ago. One of these discoveries refers to galaxies with redshifts between 9 and 11. But what does that mean? Simply put, redshift measures how much the light from these galaxies has been stretched by the expansion of the universe. The greater the redshift, the further back in time we look. The light from these newly discovered galaxies began its journey when the universe was less than 1 billion years old. At that time, our Milky Way was just beginning to form, and only the first stars illuminated the cosmos. These galaxies are not only incredibly distant, but also incredibly young, allowing us to glimpse the formative ages of the universe. So how did galaxies like ours originate and evolve over billions of years? Let's find out. In the depths of space, hidden among countless stars, is Sears 43833. This galaxy, located at a redshift of 876, transports us to an era when the universe was less than 600 million years old. Its light, traveling through the vastness of space, provides us with valuable information about the early stages of galaxy formation. Looking further, astronomers have approached Sears 16943, an even more distant galaxy with a redshift of 11. For this galaxy is one of the oldest ever observed, as it emitted its light when a universe was only 400 million years old. The study of such distant galaxies helps us understand the processes that led to the formation of the first stars. Finally, Max 0647DJD appears before us, observed with a redshift of 10.17. The light from this galaxy has taken more than 13 billion years to reach us. Its discovery has been possible thanks to the powerful capabilities of the JWST, which has revealed its complex structure and provided information about the early universe. But what is redshift and why is it so important? Imagine a car driving away from you. As the car drives away, its taillights appear increasingly red. The taillights become increasingly red as it moves away from us. The light from distant galaxies stretches and shifts toward the red spectrum. The greater the redshift, the more distant and ancient a galaxy is. Redshift is an essential tool for astronomers, as it allows us to measure the distance to these galaxies and, therefore, their age. The light from these galaxies began its journey billions of years ago, creating a snapshot of the early universe's stages. When studying galaxies with different redshifts, we can reconstruct the history of cosmic evolution. The galaxies are not only distant objects, they are time capsules that allow us to glimpse the early universe. These discoveries address fundamental questions about our existence. How are the first galaxies formed? What processes drove their evolution? And what does this tell us about our Milky Way? The discovery of these distant galaxies has been possible thanks to two important observation programs. These programs use the advanced capabilities of the James Webb Space Telescope to observe the universe more deeply than ever. The first program used the discretionary time of the director to focus on the observation of galaxies with high red shift, under the direction of the principal investigator Pablo Arabellero. The objective of this program was to study the early universe in search of galaxies formed a few 100 million years after the Big Bang, focusing on specific regions of the sky. DD 2750 successfully identified several ancient galaxies, including Sears 43833. The second program was part of a global observation program led by principal investigator Dan Company. This program aimed to carry out detailed spectroscopic studies of known galaxy candidates with high redshift. The GO 1433 program was fundamental to confirming the redshifts of these galaxies and studying their properties in detail. As part of this program, the team observed two other objects and obtained valuable data on their composition and structure. The JWST used two of its most powerful instruments, the NIR SPEC and the NIR CAM, to carry out these revolutionary observations. Let's take a closer look at how these instruments work. The NIR SPEC, or near-infrared spectrograph, is designed to simultaneously obtain spectra of multiple galaxies. This instrument can analyze the light from galaxies to determine their chemical composition, temperature, density, and redshift. This instrument is crucial for studying the detailed properties of galaxies and understanding their evolution over time. The NIR SPEC operates in the near-infrared, which is ideal for observing distant galaxies. By dividing the incoming light into its constituent wavelengths, the instrument creates a detailed fingerprint of each galaxy, revealing its unique characteristics. The NIR CAM, or near-infrared camera, has a different but complementary function. It takes high-resolution images of galaxies, allowing astronomers to study their morphology and structure. The camera is especially effective at observing faint and distant objects, making it indispensable for identifying and analyzing galaxies with high redshift. The wide field of view of the NIR CAM allows capturing large areas of the sky in a single image. This capability is fundamental for studies such as DD 2750 and GO 1433, in which astronomers need to observe many galaxies simultaneously. By combining detailed spectra with high-resolution images, scientists can build a complete picture of these ancient galaxies. So, what exactly did the scientists see? These ancient galaxies are incredibly small compared to our Milky Way. They are less than 1 kiloparsec in diameter, making them about 1,000 times smaller than our Milky Way. Despite their tiny size, they're full of activity, typical of young star-forming galaxies in the early universe. Some of them even present complex structures affected by gravitational lensing, a phenomenon in which a massive object in the foreground distorts the light of an object in the background, allowing us to see them in greater detail than would otherwise be possible. But why are these size differences important? It is precisely the small size of these galaxies that suggests they are in the early stages of their evolution. In a young universe, galaxies were still forming and merging, which led to intense periods of star formation. These compact galaxies are like snapshots of the early universe that show us how galaxies begin their life and how they grow over time. What are these galaxies like? Sears 43833, for example, looks like a compact and bright object with hints of structure indicating regions of intense star formation. Sears 16943, although smaller, also shows signs of active star formation. In contrast, MAX 0647DJD shows a more complex morphology due to the lens effects and shows multiple images of the same galaxy. However, it is understanding the light from these galaxies that is key to unlocking their secrets. This is where the spectral energy distribution, or SED, comes into play. The SED represents the range of energy emitted by a galaxy in different wavelength ranges, from ultraviolet to infrared. By studying the SED, astronomers can infer various physical properties of a galaxy, such as its age, mass, and star formation rate. We use the data from NIR-SPEC and NIR-CAM in JWST to create the SED. Then we can model it using software that simulates different scenarios of galaxy formation and evolution by fitting the observed data to these models. We can estimate the stellar mass of the galaxy, its star formation history, and other important parameters. The SEDs of these galaxies indicate a relatively young stellar population with intense star formation that occurred less than 100 million years ago. A detailed analysis of these SEDs helps us reconstruct the life history of these ancient galaxies, as we have already mentioned. The light from these distant galaxies contains a large amount of information, especially in the form of emission lines. Emission lines are bright lines that appear at specific wavelengths of the spectrum and are produced when elements in the galactic gas are energized and emit light. Each element produces a unique set of lines, very similar to a fingerprint, which allows us to determine the chemical composition of the galaxy. In addition to identifying the elements, the emission lines also reveal the physical properties of the gas and stars of the galaxy gases and stars of the galaxy. When analyzing the intensity and proportion of these lines, astronomers can estimate the star formation rate, which shows how many stars are born in a galaxy. For example, a strong Hal-alpha emission line indicates a high rate of star formation, indicating that the galaxy is actively producing new stars. The emission lines also help determine the oxygen content of the galaxy, which is an indicator of its overall metallicity. This tells us how many generations of stars have existed, enriching the galaxy with heavier elements over time. Understanding these properties helps us compile the history of the galaxy and determine its stage of evolution. One of the most intriguing characteristics observed in these distant galaxies is the damped Lyman alpha, or D. But what exactly is D? Simply put, the D is a broad absorption line in the spectrum of a galaxy caused by the presence of large amounts of neutral hydrogen gas. This absorption line is broader than normal lines, indicating a significant amount of gas. DLAs are important because they allow us to directly measure the amount of neutral hydrogen in the early universe. This information helps us understand how galaxies acquire the gas that fuels star formation and how they evolve. By studying D, we can learn about the conditions of the universe when these galaxies formed. The detection of D in these galaxies involves analyzing their spectra in search of broad absorption features. This process allows us to quantify the amount of gas present and understand the environment around young galaxies. The presence of D in these galaxies tells us that they are rich in neutral hydrogen, which is crucial for star formation. It also provides information about the intergalactic medium, the space between galaxies, and its role in galaxy formation. By comparing the characteristics of D with those of different galaxies, we can build a more complete picture of the early universe. The discovery of these ancient galaxies offers a unique opportunity to compare them with other known superluminous galaxies. What makes these new discoveries special is the unusual amount of dense gas that surrounds them. This gas, composed mainly of hydrogen and helium, is among the first elements that existed in the universe. The presence of such dense gas is unusual, as it indicates that these galaxies are in their early stages of evolution. This dense gas is likely to fuel the formation of new stars, playing a crucial role in their evolution. Another unique characteristic of these galaxies is their low metallicity. In astronomy, metallicity refers to the content of elements heavier than hydrogen and helium in a galaxy. The low metallicity also confirms that these galaxies have not gone through many cycles of star formation, which means that they have fewer heavy elements and are in the early stages of their evolution, making them an ideal laboratory to study the initial stages of galaxy formation and their evolution. This information will help us reconstruct the sequence of events that led to the formation of galaxies in the early universe. These discoveries also fit into the broader context of understanding the history of the universe. During the period known as the era of reionization, the universe went from opaque to transparent. The galaxies discovered by the JWST are among the first to contribute to the reionization process by ionizing the surrounding gas. The next steps will be to create large statistical samples of galaxies to estimate in detail the prevalence and brightness of their characteristics. Researchers will continue to study where the gas is, how much is near the center of the galaxies, and whether it is primordial or already contains heavier elements. Meanwhile, we will wait for new results and discoveries, which we will not hesitate to communicate to you. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. Pluto, once considered the ninth planet, and now occupying a separate category at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant point on the edge of our vision, a world waiting to be discovered, guarding its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedented and ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, vast nitrogen glaciers, and a legendary Tombaugh Regio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us on this journey to the icy depths of the outer solar system, where a dwarf planet eagerly awaits to tell its story. In the early 20th century, the search for the ninth planet, the mysterious Planet X, captivated the world of astronomy. The search was not limited to adding another name to the list of planets, but was about understanding the invisible forces that shape the orbits of the then-known celestial bodies. At the center of the search was the Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on an arduous journey through space armed with a telescope and photographic plates. Tombaugh set out to scrutinize the night sky inch by inch in search of an elusive planet that eluded detection. On a night in February 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a small speck of light unlike anything he had observed before. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. Over the decades, the Hubble Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lenses pierced the veil of distance that separated us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a simple bright spot to a world with distinctive characteristics. These Hubble images laid the foundation for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, which hinted at a dynamic world waiting to be explored. An odyssey of discovery that began with a simple flickering point on a photographic plate has led us to a new frontier. Pluto, which was once a mere curiosity in the confines of our solar system, was about to reveal its secrets thanks to a tireless search for knowledge and an implacable spirit of exploration. 5, 4, 3, 2, 1. Ignition and liftoff. The NASA spacecraft New Horizons embarked on a decade-long journey to visit Pluto and beyond. In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no larger than a grand piano, was suspended in the vastness of space, heading toward a world barely visible to the human eye. Its mission is to unravel Pluto's secrets, a mysterious dwarf planet located at the edge of our solar system. As New Horizons soared into the sky, It carried the aspirations of countless people who had dedicated years to that moment. The journey was a cosmic marathon that lasted almost a decade and covered more than 3 billion kilometers. With precision, it charted a route through the void, guided by the gravity of the celestial bodies that crossed its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the world watched with great expectation. The first images were simply revolutionary. Pluto, previously just a point of light even with the most powerful telescopes, now looked like a world of mountains, valleys, and plains. The landscape that was visible was surprisingly varied. Mountains of ice, some as high as the Rockies, stood proudly on the surface, with their peaks wrapped in a blanket of methane snow. Sputnik Planitia, a plain of nitrogen ice, stretched across the dwarf planet, its surface shaped by a complex pattern of ridges and depressions. Among the most surprising discoveries are indications of geological activity. Pluto, long believed to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice flowed slowly through the landscape, and indications of cryovolcanoes indicated that this distant world was not as inactive as thought. New Horizons jumped into the unknown and bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes, but a dynamic world full of surprises and beauty at the edge of our solar system. It was only the beginning of a new chapter in our understanding of the cosmos. Pluto's extensive surface is home to one of its most fascinating features, Sputnik Planitia, a huge heart-shaped glacier. It is not only a striking visual landmark, but a geological marvel that has changed how we think about this distant world. The origin of Sputnik Planitia is a story of cosmic forces. It is believed that this vast basin, which extends more than 650 miles, was formed by the impact of a huge celestial body that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, rotating and flowing in response to the faint heat coming from Pluto's interior. This process, similar to a lava lamp, demonstrates that Pluto is far from the frozen, inert world we imagined. More mysteries lie hidden beneath the icy facade of Sputnik Planitia. The uniform distribution of mass in this region, obtained from spacecraft measurements, suggests the presence of a denser layer beneath the ice. Scientists speculate that it could be an underground ocean. It is possible that this deposit contains liquid water isolated by the ice crust covering it. Among other discoveries, scientists have also found that Pluto has an atmosphere floating above its icy surface, as thin and fragile as an atmosphere can be in the cold confines of the solar system. Composed mainly of nitrogen, with traces of methane and carbon monoxide, this fine veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere is complex. Initial expectations when New Horizons flew by were to find an atmosphere extending hundreds of kilometers above the surface, much more extensive than expected. This thin atmospheric layer is stratified and presents a complex interaction of gases that scatter and refract sunlight, creating a fascinating blue hue that resembles Earth's sky. Pluto's journey around the Sun is different from that of any other planet in our solar system, with an unimaginable orbital period of 248 Earth years. Each season on Pluto can last for decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is inclined at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, although faint, is enough to cause a remarkable transformation. The surface, composed of nitrogen, methane, and carbon monoxide, begins to sublimate, a process by which these ices pass from a solid to a gaseous state without passing through an intermediate liquid state. This sublimation is more pronounced in the regions exposed to the weak but constant sunlight, causing an increase in atmospheric pressure as the gases previously trapped in the ice are released. This degassing thickens Pluto's atmosphere, making it more substantial during these warmer periods. The atmosphere expands, rising hundreds of kilometers above the surface, much further than during the colder periods. This expansion is uneven and influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey away from the Sun and toward more distant parts of its orbit, the atmosphere undergoes a dramatic change. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining characteristic of Pluto's climate and transforms its surface over the centuries. The dance of ice and vapor that unfolds throughout Pluto's long year paints a portrait of a world in constant motion, far from a frozen and static wasteland. Pluto's surface is a dynamic environment that reminds us of the active and changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational poles that protect the atmospheres of the largest planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric cape contributes to the tail of ionized gas, an invisible wake similar to a comet that Pluto leaves as it orbits the Sun. This leak is not a constant, smooth flow, but a complex interaction with the solar wind, a stream of charged particles emanating from the Sun. These particles, when colliding with the escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of the solar and planetary forces unfolds. From the dynamic atmosphere and unique climate of Pluto, we move on to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer solar system. Charon, the largest satellite of Pluto, orbits in sync with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world, a world full of geological wonders and a unique history that is intertwined with that of Pluto. When New Horizons flew over Charon, it saw canyons so deep and wide that they could easily swallow parts of Earth's Grand Canyon. These abysses extend across the satellite's entire surface and tell a story of geological upheaval. The mountains, which rise dramatically against the lunar surface, reveal a dynamic history. They cast long shadows over the valleys that stretch at their feet. The origin of Charon's spectacular topography lies in its past, marked by internal processes and, possibly, by cryovolcanism. As Charon cooled and compressed over millions of years, it split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the surface of the moon flexed and broke the surface of the moon, pushing some areas upwards and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit, which means that Charon always looks towards Pluto and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit their planets, Pluto and Charon orbit a point in space between them known as the barycenter. This unique arrangement challenges conventional definitions of planets and moons, suggesting a binary system in which both bodies are companions in their celestial tandem. This gravitational association extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. The presence of Charon stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system provides us with valuable information about the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands as a sentinel on the edge of our solar system. This region, a vast cluster of icy bodies that extends beyond Neptune's orbit, is a relic of the early solar system and contains the keys to understanding the formation and evolution of our cosmic neighborhood. Pluto, once believed to be the ninth planet, has found its relatives among the vast number of objects in the Kuiper Belt or KBOs, such as the dwarf planets Haumea and Makemake, to smaller and lesser-known bodies. Each KBO has its own story that contributes to completing the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflects the complexity and diversity of the Kuiper Belt. The Kuiper Belt is a window to the past, a frozen archive of the solar system's birth. The objects that compose it, including Pluto, are vestiges of the era of planetary formation, untouched by the sun's heat. Its composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. The exploration of Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, such as the New Horizons flyby of Pluto, is unveiling layers of mystery and revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influences the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting Neptune's environment. However, the New Horizons exploration did not end there. After its historic flyby of Pluto, it continued its path towards a Kuiper Belt object, which it encountered on January 1st, 2019, marking the next milestone in space exploration. Arrokoth, which resembles a clay snowman, demonstrated the smooth fusion of two primordial objects, offering an unprecedented vision of the basic components of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe called Bennu is not a unique shape, but a cluster of a dozen rocks more than 3 m wide crowded around a central plate. This cluster refutes previous ideas about high-speed collisions in planetary formation and suggests, instead, a gradual fusion at speeds of less than a dozen feet per second. This intricate interaction between two lobes that lose angular momentum and smoothly merge forms an image of a patient cosmos, where the basic components of the planets come together in a celestial cycle of gravity and time. Looking ahead, the horizon of solar system exploration is filled with potential concepts for the next New Horizons missions, sparking the imagination of scientists and engineers. One of them foresees an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing a comprehensive study of the dwarf planet and its satellites. These missions could use electropropulsion that replicates the success of NASA's Dawn mission and could go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies, such as direct fusion thrusters, promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report entitled Fusion-Enabled Pluto Orbiter and Lander from NASA's NJC Innovative Advanced Concepts program describes a mission to Pluto with a direct fusion thruster using a fusion reactor. A 1,000-kilogram orbiter could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten travel time, opening new pages in the exploration of the distant worlds of our outskirts as we travel through the vastness of space, exploring distant worlds and discovering the secrets they hide. Our understanding of the cosmos continues to evolve. The history of Pluto, from its discovery to the present, vividly reminds us of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248th orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief period of time, defying the vision of its position as the ninth planet. This crossing of orbits, when Pluto and Neptune change places, occurs due to the elliptical trajectory of Pluto's orbit and its relative inclination to the plane of the solar system. Despite this temporary change, Pluto's overall trajectory ensures there is no risk of collision with Neptune due to their orbital resonance. The prolonged debate about Pluto's planetary status has long sparked discussion and controversy that extends beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, leading to Pluto's reclassification as a dwarf planet. This moment not only marked a turning point for Pluto, but also catalyzed the reclassification of other celestial bodies. The history of Pluto is closely linked to the Kuiper Belt, a region full of objects that blur the lines between planets, moons, and smaller celestial bodies. The study of Pluto and its neighbors makes us think about the wide range of characteristics celestial bodies can possess, from their atmospheres and geology to their orbits and interactions on the great canvas of the cosmos. Each thread, from the smallest asteroid to the most powerful gas giant, plays a key role in the history of our solar system as we stand on the threshold of new explorations. The legacy of Pluto and the knowledge acquired in the Kuiper Belt serve as beacons, guiding us toward a deeper understanding of our place in the universe. Rethinking our cosmic neighborhood is not just about the labels we assign, but about embracing the diversity and complexity of the universe. Surely you've already heard about black holes, which can be so massive that they dwarf entire galaxies, but some are so mobile that they wander through the Milky Way like cosmic ghosts, undetectable, of course. Perhaps you are confused or even fascinated by the fact that the black hole closest to Earth is not as far away as you think, and that when these cosmic giants collide, they generate frequencies as unique as fingerprints, frequencies that could be the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in ways much more complex than we had ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the cosmos. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we are familiar with small black holes, the remains of dying stars, and the supermassive ones that lurk in the hearts of galaxies, there's an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the closest globular cluster to Earth. What it discovered was nothing short of revolutionary: a black hole with a mass approximately 800 times greater than our Sun's. This celestial object is located at a distance of between 6,000 and 7,200 light-years from us. Why is this so important? Well, for years, astronomers have struggled with a gap in the black hole family tree. We had evidence of both the existence of small black holes with a few times the mass of our Sun and supermassive black holes with masses of millions or billions of solar masses. But intermediate mass black holes turn out to be the missing link, mysterious relatives that everyone has heard of but no one has seen. An equally interesting question is how these intermediate mass black holes form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when merging with larger galaxies. Another theory states that they could have formed from the collision and fusion of smaller black holes. Identifying these elusive black holes is no easy task, as it requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the movement of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played a key role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of the stars orbiting this massive object, scientists have been able to estimate its mass. It is like understanding the character of an invisible puppeteer by observing the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative, as they could be key elements in the formation of galaxies and even hold clues about the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on a new meaning. While our closest celestial neighbor, the Moon, is only 238,857 kilometers away, the European Southern Observatory, ESO, made headlines by announcing the discovery of a black hole in the HR 6819 system, located only 1,000 light-years away. This would make it the closest black hole to Earth, but this claim was later disproven. Subsequent research by Abigail Frost from the University of Leuven, Belgium, discovered that HR 6819 does not contain a black hole, but rather a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This discovery was more than just a correction, as it opened up new possibilities for studying stellar evolution and interactions after the expulsion from HR 6819. The title of closest black hole to Earth then became Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. Gaia's main task is to map the Milky Way with unprecedented detail, and it was thanks to this meticulous work that Gaia BH1 was discovered as the closest black hole to Earth. Gaia BH1 offers a unique opportunity for scientific observation and research. Its relative proximity allows for more detailed measurements and can help answer fundamental questions about the properties of black holes, such as their mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on various observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more precise these instruments must be to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific importance, the idea of a nearby black hole captivates the public's imagination, makes the cosmos more relatable, and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the center of galaxies or in binary star systems. But what happens when a black hole is left wandering the universe alone, without connection to any galaxy or star? What makes these black holes go rogue, and how do astronomers manage to find such elusive objects? Let's delve into the mysterious world of rogue black holes together. The scientific community was thrilled when astronomers announced the first clear discovery of a wandering black hole located 5,000 light-years from Earth. This black hole weighs 71 times the mass of our Sun and moves at a speed of about 28 m per second. The key to this revolutionary discovery lies in a phenomenon predicted by Einstein's general theory of relativity, known as gravitational lens. When a massive object like a black hole passes in front of a background star, its intense gravitational field deflects the light from that star, creating a brief brightening phenomenon. This is how this rogue black hole was discovered. As we know, the birth of a wandering black hole is a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses and causes a supernova explosion. The energy released can be so enormous that it ejects the newly born black hole from its stellar cradle, sending on a journey through space. This is probably how our newly discovered wandering black hole began its cosmic journey. What is even more intriguing is the speed at which this wandering black hole travels, about 28 m/second, a high value relative to the stars. This speed is probably the result of the impact from a dying massive star that sent it on its solitary journey. The discovery of this solitary black hole is just the tip of the iceberg in future missions, such as those of the European Space Agency's Gaia Telescope, and NASA's Nancy Grace Roman Space Telescope. Astronomers hope to find even more space travelers of this kind. These future discoveries will not only increase the number of known wandering black holes, but also refine our theories about their properties and frequency. Each galaxy is like a cosmic dance floor where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm of the entire galaxy. Research published in the monthly notes of the Royal Astronomical Society shows that galaxies and their central black holes grow together regardless of their location. Astronomers have long been puzzled by the relationship between a galaxy's mass and its central black hole. Both seem to be aware of each other, even though the black hole is much smaller than the galaxy it resides in. This relationship implies a deep cosmic connection, a kind of codependency in which the growth of one affects that of the other. One of the most intriguing questions in astronomy is what came first, the galaxy or its center? The answer remains difficult to determine still. However, what is clear is that a close connection was established quickly on a cosmic scale, paving the way for a complex interaction between growth and evolution. Let's delve into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries packed with the raw materials needed for star formation and black hole growth. Studies show that these galaxies, known as blue nuggets, have exceptionally high rates of star formation. They feed on nearby gas streams that not only accelerate star formation, but also contribute to the rapid growth of their central black hole. When black holes feed, they become active. The gas around them heats up and emits powerful radiation. This heated gas is less likely to collide with the black hole, creating a feedback loop that stabilizes the black hole's size. However, as the galaxy grows, it can push more gas towards its center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows more slowly, and if it is too small, it catches up because of the abundance of gas and dust in the galaxy. Therefore, some galaxies defy the norm. These blue nuggets, despite their small size, have large central black holes. As these galaxies age, their star formation stops and they become red nuggets, retaining their enormous black holes still. As we delve into the abyss of the black hole, it becomes evident that young, gaseous galaxies serve as the birthplace of various phenomena related to black holes. Whether they are luminous black holes, intermediate mass wandering black holes rushing through space, or the black holes closest to Earth, their origins often go back to these bright young galaxies. Understanding the cradle of these cosmic giants helps us unravel the mysteries that black holes hold within. Now, let's look at something rare. There's a situation in which black holes collide, and in doing so, create a cosmic symphony of gravitational waves that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometry Gravitational Wave Observatory in 2015, opened a new frontier in astronomy research. However, recent research shows that these waves interact in complex ways as they propagate, which tests our understanding of gravity and general relativity. Traditionally, scientists have used linear models to describe these waves' behavior. However, a new study has revealed nonlinear effects that reveal a more complex picture, like the difference between a calm pond and a rough sea. In a calm or linear pond, throwing a stone creates an isolated wave, while in a rough or nonlinear sea, multiple forces interact to create complex patterns. When black holes collide, they emit unique frequencies or chirps, music. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of the colliding black holes. They offer a new way to test the limits of general relativity and may even provide clues about the nature of dark matter itself. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course now. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge together. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem together. These colliding dwarf galaxies offer a vision of the early universe, which was full of similar small galaxies then. Most of them ended up merging to form larger galaxies like our own, the Milky Way. Milky Way. Understanding these processes helps us reconstruct the cosmic mystery of galaxy and black hole formation. As we delve into the abyss of black holes, we discover that each type, from luminous intermediate mass black holes to wandering black holes hurtling through space, plays a unique role in this grand cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena, and, of course, each discovery, from the frequencies they generate to the very nature of gravity, will undoubtedly add a new layer to our understanding of the universe. As our telescopic eyes become sharper and computational models more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal in the 21st century. Humanity is at a crossroads, a moment in history when we can see the stars, but still cannot touch them. Born in the era between the exploration of our own planet and the possibility of reaching other worlds, we find ourselves on the threshold of an extraordinary journey. It's not just about rockets or physics, but about our survival and place in the universe. Let's imagine a future in which Earth faces an existential threat. A catastrophe, collision with an asteroid, climate collapse, or something unpredictable. Our solution: to build generational ships, colossal spaceships that serve as floating cities where multiple generations are born, live, and die while traveling to another star, to a new home. Einstein's special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of light speed. The generational ships that travel to a special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of the speed of light. Generational ships, traveling at a significant fraction of the speed of light, could travel great distances between the stars with technologies such as matter and antimatter engines, compact fusion thrusters, and even black hole propulsion. What seems like science fiction could become reality, but these ships are not just boats, they're lifeboats for humanity. They must sustain life for centuries, perhaps millennia, facing the challenge of space travel, genetic diversity, and mental health. Each ship will be a microcosm of Earth, with its social structures, cultural heritage, and daily challenges. What would it take to build a ship like that? How could its inhabitants survive and thrive? Join us as we delve into the complexities of interstellar travel without exceeding the speed of light. Today, we will try to unravel the secrets of how humanity may one day travel to the stars, but not in an instant, but over generations. Planning interstellar travel is not only a matter of technology, but also of predicting why it might be necessary. Foreseeable threats to the survival of humanity could force us to seek refuge outside our solar system. Understanding these threats will help us prepare for possible future scenarios that could force humanity to embark on such an extraordinary journey. One of the most immediate threats comes from space itself. Comet impacts throughout Earth's history, collisions with comets and asteroids have caused mass extinctions and major climate changes. A strong enough collision could make Earth uninhabitable, forcing us to seek a new home among the stars. Another threat is climate collapse. Human activity has already caused significant changes in our climate: rising temperatures, melting ice caps, and increasingly severe weather phenomena. If these trends are not controlled, Earth could become hostile to human life, making the search for habitable exoplanets a top priority. Technological progress, while bringing enormous benefits, also carries significant risks. Advances in artificial intelligence, biotechnology, and autonomous systems could lead to scenarios in which humanity faces a threat from its own creations. Uncontrolled artificial intelligence or genetically modified pathogens could become existential risks, leading to the need to establish human colonies on distant worlds as our species searches for a new home. Proxima and TB are leading candidates, located only 424 light-years away in the Alpha Centauri system, and are the closest known exoplanets located in the habitable zone of their star. As many know, this zone, often referred to as the Goldilocks zone, is the area around a star where conditions may be optimal for the existence of liquid water, an essential ingredient for human life. Proxima Centauri b was discovered in 2016 and has been the subject of intense study ever since. It orbits a red dwarf star that is smaller and colder than our Sun, which means that the planet would have to be much closer to the star to be in a habitable zone. This proximity, although favorable for retaining heat, also exposes the planet to eruptions and radiation, which must be taken into account when considering human colonization. Current research indicates that the planet has a mass similar to that of Earth, and that it could have a rocky surface, but much is still unknown about it, including the composition of its atmosphere and the presence of liquid water. Future missions and observations will be necessary to collect more data and assess its suitability for life. Sending a spacecraft to our nearest star involves not only covering the distance, but also ensuring that the destination is suitable for human life. This requires a multifaceted approach that includes robotic probes and telescopes to collect detailed information about the planet's environment. These missions will help determine the feasibility of establishing a human colony and the preparations necessary for long-term survival. Proxima b was chosen as our target due to its relative proximity and potential habitability. However, reaching and inhabiting that distant world will be a monumental task that will require an unprecedented level of planning, innovation, and collaboration. The dream of exploring the stars has always been tempered by the harsh realities of physics and time. Traditional concepts of space travel, in which a crew departs and arrives at its destination within their lifetime, seem increasingly impractical when it comes to the vast distances between stars. This is where the concept of intergenerational ships comes into play, a bold and innovative solution to the problem of long-distance space travel. Generational ships, also known as intergenerational ships or generation ships, are designed to keep people alive for centuries or even millennia. These ships are self-sufficient ecosystems with not only a crew on board, but all their descendants. Life on a generational ship is designed to mimic a small, autonomous world with living areas, food production, water recycling, and social systems. The concept is simple, but profound. As the original crew ages and eventually dies, their children and the children of these continue the mission. This life cycle guarantees that, for generations, the ship will continue its journey, and each new generation will be trained and prepared to maintain the ship and reach its destination. This approach to space travel requires careful planning and robust systems to ensure the inhabitants can survive and thrive. Every aspect of life must be carefully considered, from genetic diversity to ensure a healthy population to cultural and educational programs that transmit vital knowledge and skills. Einstein's special theory of relativity poses a problem for traveling faster than light. According to this theory, as objects approach light speed, their mass increases and they require exponentially more energy to accelerate. This makes traveling faster than light practically impossible with our current understanding of physics. Generational ships offer a practical solution within the framework of Einstein's theory by accepting the duration of space travel and planning generations of life aboard such ships. Humanity can aspire to reach distant stars. This approach recognizes the limitations imposed by relativity, while supporting the resilience and adaptability of the human spirit. Traveling to the stars requires overcoming significant challenges, among which the enormous distances between celestial bodies stand out. For interstellar travel to be viable over the course of a human life, we must take a closer look at advanced propulsion techniques and the intriguing phenomenon of relativistic time dilation. Relativistic time dilation is a consequence of Einstein's special theory of relativity. When an object approaches the speed of light, time aboard slows down compared to the time experienced by an observer at rest. This means that, for a spacecraft traveling at a significant fraction of the speed of light, the crew's travel time will be shortened compared to those who remain on Earth. For example, if a ship could travel at 90% of light speed, time dilation would make 1 year aboard the ship equivalent to over 2 years on Earth. Due to this effect, interstellar travel that lasts decades or centuries may seem shorter to the crew, although it does not shorten the distance. Several advanced propulsion methods have been proposed to reach the high speeds required for interstellar travel. Each method has its own problems and potential advantages. For example, antimatter propulsion involves the annihilation of matter and antimatter, releasing enormous amounts of energy. This reaction releases energy much more efficiently than chemical rockets, which could allow spacecraft to reach significant fractions of the speed of light. However, producing and storing enough antimatter remains a major technical obstacle. On the other hand, compact fusion reactors use nuclear fusion, the same process that powers the sun, to produce energy by combining light atomic nuclei with heavier nuclei. These reactors could provide sustained and powerful thrust for spacecraft. Although controlled fusion technology is promising, it is still in development, and building a compact and reliable reactor for spaceflight is another major engineering challenge. Black hole propulsion is a more speculative concept that involves harnessing the gravitational energy of a black hole to propel a spacecraft. The idea is to create a small artificial black hole and harness the energy from the Hawking radiation it emits. In theory, this method could provide continuous and powerful acceleration, but the technology to create and control artificial black holes remains far beyond our current capabilities. However, the problems do not end there. Propellants traveling at speeds close to light speed are fraught with dangers. One of the main ones is the threat posed by interstellar particles. At these speeds, even the smallest particles can cause significant damage upon collision. Spacecraft must be equipped with advanced shielding to protect against these high-energy collisions. Radiation is another serious danger. High-speed space travel exposes the crew to intense cosmic radiation that can have harmful health effects. Effective radiation protection and medical intervention will be necessary to maintain the crew during long-duration missions. Maintaining the structural integrity of the spacecraft long-term is also essential. The stresses and strains of high-speed flight can weaken materials over time, requiring advanced construction techniques and regular maintenance to keep the spacecraft safe and functional throughout the journey. Despite these formidable challenges, the pursuit of interstellar travel drives human ingenuity and ambition. Music, by researching and developing advanced propulsion techniques and overcoming the dangers of high-speed travel, we are taking crucial steps to reach the stars and expand our presence in space. Choosing the right propulsion system for interstellar travel is one of the most important decisions in missions planning. The propulsion system determines the speed, duration, and feasibility of the mission, so it is important to explore both best practices and traditional methods. A promising approach is to expand traditional propulsion technologies. NASA's Parker Solar Probe uses a combination of chemical propulsion and gravity assist to reach unprecedented speeds. The probe travels at more than 430,000 miles per hour, which is approximately 0.064% of the speed of light, making it the fastest man-made object to date. Its propulsion system is based on solar-powered hydrogen thrusters, which has demonstrated the potential of existing technology for high-speed space travel. Gravity assists or slingshot maneuvers use the gravity of planets or other celestial bodies to increase a spacecraft's speed without expending additional fuel. Through careful trajectory planning, a spacecraft can gain speed, reducing travel time across great distances. Although this technique is not sufficient on its own for interstellar travel, it can be an important component of a multi-stage propulsion strategy. Expanding these traditional technologies involves developing more efficient thrusters and larger amounts of fuel. Another promising area is innovation in ion thrusters, which use electric fields to accelerate ions and create thrust. Ionic thrusters are very efficient and can operate for long periods, making them suitable for long-duration missions. The combination of these advanced conventional methods, could be a practical solution for the initial stages of interstellar travel. To travel faster, we must consider more advanced propulsion methods, like nuclear propulsion. One of the most intriguing concepts in this category is Project Orion, initially proposed in the 1950s. This method consists of a series of thermonuclear explosions behind the spacecraft, each creating a powerful thrust to propel the ship forward. Project Orion uses a huge pusher plate at the rear of the ship, designed to absorb shock waves from the explosions and convert them into forward momentum. By repeating this process in a controlled manner, the spacecraft will be able to reach significant fractions of light speed, drastically shortening the flight time to nearby stars. Although the concept is theoretically sound, many technical and safety problems still need solving. Controlling the timing and direction of explosions requires precise design, and the spacecraft must, in turn, be designed to withstand enormous loads. In addition, the environmental impact of launching such a vehicle from Earth must be carefully considered, possibly requiring space launch platforms. Another fusion engine concept is the Daedalus project, which involves using fusion reactions to propel a spacecraft. This method involves the use of small fusion fuel pellets, such as deuterium and helium-3, which are ignited by electron beams to create a constant thrust. The Daedalus project aims to reach speeds of up to 12% of the speed of light, which would allow travel to the nearest stars over the course of a human life. Fusion propulsion offers a more controllable and potentially safer alternative than the Orion method. However, the technology to build reliable and efficient fusion reactors for spaceflight is still in the development phase. Significant advances in fusion research and engineering are needed to make this approach viable for interstellar missions. Choosing the right propulsion system is a balance between feasibility, performance, and safety. Traditional methods, such as those used in the Parker Solar Probe, offer practical short-term solutions, while advanced fusion propulsion concepts, such as the Orion and Daedalus projects, promise the possibility of faster and more ambitious interstellar travel, ensuring the survival and health of the crew for several generations. One of the most important aspects is maintaining genetic diversity, necessary to avoid inbreeding and genetic diseases that could endanger the mission. To solve the problem of genetic diversity, scientists use Monte Carlo simulations. These models use statistical methods to simulate and predict genetic variability over generations, introducing various parameters, such as initial population size, mutation rates, and reproductive patterns. These simulations can provide information on the genetic health of a population over time. Monte Carlo simulations help determine the minimum population size needed to maintain genetic diversity and prevent inbreeding depression. They also take into account possible random events, such as accidents or diseases, that could affect the population. This type of model is essential for creating a sustainable human colony that can thrive for centuries. Maintaining genetic diversity requires careful planning of reproductive strategies and potential genetic screening. The crew must be trained on the importance of genetic health and the measures needed to maintain it. This includes monitoring genetic diversity and making informed decisions about relationships and reproduction. Research shows that a minimum initial population of at least 100 individuals is required to maintain genetic health for generations. This figure comes from studies conducted by scientists such as Frederick Moran and Camille Balliet, who have extensively studied the genetic dynamics of small, isolated populations. Moran and Balliet use Monte Carlo simulations to explore different scenarios, including different population sizes and reproductive strategies. Their study shows that, with a balanced sex ratio and an optimal reproductive rate, an initial population of at least 100 individuals can maintain a healthy gene pool. This population size ensures that genetic drift and inbreeding do not endanger the health and viability of future generations. An initial population of 100 individuals should grow to 500 over generations. This growth is necessary to create a stable and resilient population that can cope with unforeseen challenges. The model takes into account various factors, such as random genetic mutations, environmental influences, and possible catastrophes, to ensure the population's sustainability. Designing a generational ship to accommodate a growing population involves planning adequate living space, resources, and social structures. The ship must provide educational, health, and recreational facilities to support the physical and mental well-being of the crew. This includes spaces for collaborative activities and private accommodations to provide a balance between social interaction and personal privacy. Beyond physical infrastructure, maintaining social cohesion and cultural continuity is vital. The crew must develop a shared sense of purpose and identity to foster cooperation and sustainability. Cultural and educational programs play a key role in maintaining the knowledge and values necessary for the mission's success. Effective crew and population planning is essential for the success of a generational ship. Through advanced genetic simulations and research, we can ensure that the population remains healthy and viable. With careful planning and a commitment to maintaining social and genetic health, humanity can thrive on the path to the stars, ensuring the survival and prosperity of future generations. However, above all, designing a generational ship capable of sustaining human life for centuries involves creating a self-sufficient environment that mimics basic aspects of life on Earth. This includes creating artificial gravity, producing food, and recycling vital resources like water and air. These systems must be reliable, efficient, and capable of operating autonomously for long periods. One of the most important aspects of ship design is creating artificial gravity to maintain the health and well-being of the crew. Prolonged exposure to microgravity can lead to muscle atrophy, bone density loss, and other health problems. To counteract these effects, generational ships can use rotating means to create a centrifugal force that mimics Earth's gravity. The most practical design consists of a large rotating ring or cylindrical section where the crew lives and works. As the structure rotates at a certain speed, centrifugal force pushes occupants outward, simulating the effect of gravity. For example, a ring with a radius of 100 yards must rotate at a speed of approximately 3 revolutions per minute to create an artificial gravity of 1 g similar to that of Earth. This design not only helps maintain physical health, but also provides a familiar environment to alleviate the psychological challenges of living in space. Rotating habitats can include living areas, recreational spaces, and work areas designed to optimize the use of space and available resources. Reliable and efficient food production systems are also needed to sustain populations across generations. Hydroponic and aeroponic systems offer solutions for growing without soil, using nutrient-rich water or mist to nourish the plants. These methods are efficient and use less water and space than traditional agriculture and are well suited to the controlled environment of our ship. Hydroponic systems consist of growing plants in nutrient solutions with their roots suspended in water. Aeroponic systems, on the other hand, use a fine mist to deliver nutrients directly to plant roots. Both systems can grow a wide range of crops, from leafy greens to tubers, providing balanced nutrition for the crew. These systems can be automated and monitored to maintain optimal growing conditions, ensuring a stable and reliable food supply. In addition, genetic modification and improvement will allow us to increase the yield and nutritional value of crops. Efficient recycling of water and air is critical for the sustainability of a generational ship. Water recycling systems must be able to recover and treat wastewater, ensuring a continuous supply of clean water for drinking, cooking, and watering. Advanced filtration and purification technologies, such as those used on the International Space Station, are already reaching high levels of efficiency. For example, the water recovery system can recycle up to 98% of wastewater, including sweat and urine. This level of efficiency is necessary for long-duration missions when resupply from Earth is not possible. Future generation ships should further improve this efficiency with the goal of achieving almost complete recycling to minimize the need for large water reserves. Air recycling is equally important and requires systems that can remove carbon dioxide and replenish oxygen. Natural systems, such as plants and photosynthesis, can be integrated with artificial CO2 scrubbers to maintain a balanced atmosphere. Plants, in turn, not only provide oxygen, but also contribute to the crew's psychological well-being by providing a connection with nature. Projects like Biosphere 2 have demonstrated the potential to create closed ecosystems in which plants, humans, and microorganisms coexist by recycling air, water, and nutrients. Although Biosphere 2 faced some challenges, it demonstrated the feasibility of these systems and provided valuable lessons for designing life support systems in generational ships. Creating a self-sufficient generational ship requires integrating advanced technology with natural processes to ensure the health and well-being of its inhabitants. Artificial gravity, efficient food production, and reliable disposal systems are the pillars of this design, which will allow humanity to embark on a long-term journey to the stars, ensuring the success of a multi-generational mission that goes beyond the physical and technological aspects of the ship, since it requires satisfying the mental, social, and educational needs of pillars of this design, which allow humanity to embark on a long journey to the stars. Ensuring the success of a multi-generational mission goes beyond the physical and technological aspects of the ship, as it requires meeting the crew's mental, social, and educational needs, ensuring their health, motivation, and cohesion throughout the long journey. Isolation and confined spaces can significantly affect morale and mental health, and a lack of new stimuli and prolonged separation from Earth can lead to feelings of loneliness, anxiety, and depression. Addressing these issues is critical to maintaining crew motivation and stability. Virtual reality technologies offer promising solutions for mental health and cultural connection by creating immersive simulations of terrestrial environments. Virtual reality, or VR, can provide a sense of evasion and familiarity. Crew members will be able to see forests, oceans, and even social gatherings, which will help alleviate feelings of isolation and maintain their connection with their home planet. Artificial intelligence can also play an important role in supporting the crew's mental health. AI therapists such as Simon 2.0 from NASA can offer individual counseling, monitor psychological well-being, and suggest strategies for coping with stress and interpersonal conflicts. These AI systems can adapt and learn from each generation, providing continuity and consistency in mental health support. Ensuring the intergenerational transfer of knowledge and skills is critical to the mission's sustainability. It is necessary to establish a comprehensive educational system that ensures each new generation receives the skills necessary to operate and maintain the ship, as well as the knowledge to continue research and exploration. This should include formal education, practical training, and the preservation of cultural and historical knowledge. Embarking on an interstellar journey requires not only technological prowess, but also a deep commitment to the human spirit. By addressing the crew's mental, social, and educational needs, we ensure the resilience and connection of each generation that carries the torch of exploration and survival. Advanced technology, such as virtual reality and artificial intelligence support, combined with strong cultural and social structures, will lay the foundation for a thriving community across generations. As we reach beyond our solar system, a harmonious blend of innovation and humanity will lead us to new worlds, securing our future as an interstellar species.